Hello, everyone. We are two PhD students from Argentina. My name is Martín Ceresa, and he is Gustavo. As I said, we are two PhD students. I study functional programming, generic programming, and compiler theory, and he studies a mix between machine learning and security. So this work is going to be a mix between those areas. So I leave it to Gustavo to introduce.
Okay, thank you. Okay, so we are presenting a tool, QuickFuzz. The original paper presenting this tool was originally wrote for the Haskell Symposium, and now we have a paper on a journal in revision. So let's begin. So in this presentation, we have motivation. We are going to see QuickFuzz as a bridge between two worlds, a quick overview of our tool, a micro introduction to QuickCheck by Martín, as well as the mega deriving class instances. Finally, some limitations and current and future work. Okay, so let's start with the motivation. So what we usually want to do in general is to test programs. And this talk is a little different from the other ones, in which we are not going to test programs that were wrote with a functional language. Yes, this is one important difference. We could test, using QuickCheck, we are going to see we could test programs in Haskell and some other languages like Java, Scala, and others, because there are implementation of QuickCheck in other languages. But in this case, we create this tool to test programs that are not, in this case, in Haskell, because the tool is in Haskell. So in general, we want to detect bad things happen in programs. So that means crashes, memory leaks, all type of bad stuff. And in general, what we need to test a program is the program itself, some inputs, yes, that it should match somehow what the program is doing. It should force the program to do something, and then a property to check what we want to ensure about the program. This is, of course, quite general. We are going to see specifically what we mean about these three things. So what we want to present, in fact, a vision of two worlds. Yes, we as a Haskell programmers, we want to live in this world, in the Haskell world, in which there are types and values and libraries like QuickCheck and websites, repositories like Hackage that contains a lot of Haskell code from different applications, like reading type of images or creating HTTPS servers, whatever you want. So here we have the Haskell world in which we want to live. But unfortunately, I have to tell you, there is another world outside. I call it the real world, but well, it's just a name. And in the real world, there are many applications that are not created in functional languages or even type memory-safe languages. And I mean, like C, C++. I mean, you can use it carefully, but sometimes you can find nasty bugs. And in the real world, we have applications, and applications are usually made with libraries. And libraries sometimes contain things, issues, bugs like buffer overflow, rest conditions, memory leaks. So in the real world, we have a lot of bad stuff. We have literally dragons over there. So what we want to do is we want to create a kind of bridge. Yes, we want to be able to use things, concepts, implementation in the Haskell world, or in general in any functional language world, to test real applications and to find really nasty bugs that are in the applications that we use that are written in usually very unsafe languages. So let's start with this example that will help to clarify what I mean with real application. Let's say we have images in our browsers and programs. They are literally everywhere in the internet and I mean in any type of applications. And it's really critical to parse images in a safe way. We cannot allow buffer overflows, yes, in images because the programs that you're running in your mobile phone and your computers right now, they will automatically parse images without thinking what are the consequences of have bugs there. Yes, we assume that parsing an image is not a bad thing. Nothing bad can happen. Yes, and I mean especially things like GIF, PNG files. If you have things like SVG that are images defined with vectors, maybe they're not actually parsed by most of the programs. But for the others, it's usually the case. And if you receive an email with an image, the browser will just usually show it. Yes, so it's critical for security that we parse this correctly, and we cannot allow anything bad happening. So let's review an example that we will use to show how we use QuickFuzz to test some critical code that is parsing the GIF image, which is quite old, in fact. I think the first specification is from '89 or something, and it's still used. Somebody here familiar with the internal structure of the GIF images, or someone has programmed a parser or some code to write these type of images? Okay, well, not so much, but you can see here this is not a specification, but the structure of the records that you can have inside a GIF image, which is actually a sequence of images that we can see looping in our screens. And we have a header with some information, and then the images themselves with some particular things like color map or palette or stuff like that. So if we want to test a program that is parsing these type of images, it's critical that we know how to create them, because if you want to try to make the program to do bad stuff like a buffer overflow, you want to know which is the structure, so you should be able to test it. And we are going to show how we use Haskell libraries that are actually defining this type of images to produce files that look like GIF images, and then we can feed it into a program to test it, and we can usually crash it. So this is not what people expect. So as you can see, we need a specification of what we want to test, and this is usually the most expensive part. Where to get these specifications is because you need deep knowledge of what you are testing. And this deep knowledge is expensive because you need an expert to create to research this type of specification, and then you can test a program that will parse or print some images. So it's just a simple screenshot of the demo of our tool. In this case, I don't know if the people in the back can see. But we are testing an application inside a library made by Google. The library is called WebWP, and it's the format of images launched by Google some years ago. It wasn't so wasn't so it's not so common these days, but still it's supported by Chrome and Chromium, these type of browsers. So what we test here, we test a small command line utility called give to webp, in which we convert some file. Yes, and we actually don't care about what happened with the converted file. Yes, but we care about which is the input that we give to this program. And we're going to ask QuickFuzz to test this program with this command line will replace the two arroba symbols by the file, some random file name. And then what we want to do is we want to generate different test cases. And we want to know if the program is crashing or not. So one thing that we can see here is like the program that we want to test with the complete test case is specified there, as well as the file type that we already have supported by QuickFuzz. And then the property is that the program is not crashing, which is quite easy to detect. Yes, so let's see. These start to generate random, probably malformed GIF files, and eventually it will crash. Yes, and QuickFuzz moves the test case to a separate folder, saving how to reproduce the test case. Right? So we can see that the give to webp utility is crashing with a null pointer, which is something from the security point of view. It's not so bad. The program is just crashing and that's it. But still we don't want anyone to be able to crash our browsers just using an image. And in fact, we had results finding that we could crash Firefox with just one GIF image. It was like really instantaneous, and we give the image to the browser, and the browser just crash. So we reported these bugs together with a lot of other bugs. But let's focus in this case. So we can see here that the program is crashing. Yes. And one thing that we can ask QuickFuzz, we can ask to minimize this, because when we have a test case that is failing, we want to have the smaller test case, yes, to be able to give it to the developers, and because usually this kind of program generates a lot of useless stuff in a file, a lot of images, and one particular image in this GIF is crashing the program. So we want to try to minimize the size of the test case that we are sending to the developer, so he or she can fix the issue. Right? So in this case, QuickFuzz will just reduce using some QuickCheck techniques. He will explain very soon. It will reduce the number of bytes, yes, until it's not failing anymore, and then it will stop and say, I will be able to shrink this file, and this is the final result. And in fact, this file that is generated, if you give to another library completely different to this one that will parse GIF file, it will crash it. So this kind of inputs is really deadly for this type of programs. So now Martín will explain a little how we use Haskell, and in particular QuickCheck, to do all the magic here in this example.
OK, yes. I will tell you how do we generate all these values. We use QuickCheck, okay, as a core to our library. QuickCheck is a property-based random testing library created by Claesen and Hughes. And it requires two things. One thing is a property, which, as Gustavo told you, it is about no crashing. We have a program that is not crashing, or if it crashed, to detect it, and a way to generate values. If you want to read more about this program, you have to read that paper, which is really good. I'm going to tell you how we create these generators, these value generators, and I'm going to explain, to give an example, okay, about how we do that. So this is list. List in Haskell, you define list as a data list A, which has two constructors. One is nil, which represents the empty list, and the other one is cons, which given an A, which is going to be the head of the list, and the rest of the list of type list A, is give you back another list. So two inhabitants of this type are cons 2, cons 5, cons 7, cons 9, with nil, which is the list 1, 2, 5, 7, 9. And the other one is nil, which represents the empty list. So here is how we generate random list. In order to generate random list of type list A, we have to be able to generate randoms A's. So that's why we have an instance constraint for arbitrary A. So arbitrary is the class that uses QuickCheck to generate random values. In order to give an instance for this class, you have to define arbitrary function, which it is a gen A. Gen is the monad, which is at the core of QuickCheck library, which is basically a random monad. So to generate a list, we have to choose between an empty list and a list with at least one element. So one-off is a function that it is provided by the QuickCheck library. So choose with the same probability one of the generators in the list. So we choose with the same probability a list, an empty list, and a list with at least one element. We can extrapolate from this example that we choose between all the constructors for a given type. Okay, this type list, for example, has two ways of building a new list. One is nil, and the other one is with cons. So with QuickCheck, we can QuickCheck properties. In this case, a property is a Boolean function, which given a list A, it checks that the length of the list it is equal to the length of the reverse of that list. And as you can see, it's pretty easy to QuickCheck properties. Just QuickCheck is going to give you back a value inside the IO monad that is going to tell you that has passed all these tests. What it's doing is just generating random values, random lists in this case, and applying the function. If all the time the function returns you a true value, it is all OK. It's going to say, OK, you pass. You have passed all the tests. But here we have a very big example. This is actually taken from the GC Picture library. And this is the GIF file that Gustavo has shown you the structure a few slides before. So here we have a data GIF file, which is just a GIF file composed with all three types: GIF header, GIF image, and GIF looping. And each of these types are defined using other types, and so on and so on. You have a lot of types, and you have to give all these arbitrary instances for every one of these types. And you are going to you have to do more or less the same thing. You have to choose between each one of these constructors to create new values. So, for example, here we have GIF file. GIF file is defined using GIF header, GIF image, and GIF looping. And GIF looping is defined using other types. GIF header is using other types, and so on and so on. So you will end up defining a lot of arbitrary instances doing more or less the same thing. So we we can create an algorithm to do all this work for us. We call it mega deriving template Haskell, so megadeth for short, which recursively collects all the types involved in the generation of a single type, for example, GIF file. It's sorted up just to remove duplicates, and it creates the instances required. In this case, are going to be the arbitrary instances. But it also works for other class of instances, for example, show. So all you have to do is import the library, and megadeth is going to do all the work for you. You have to call dev arbitrary. You are going to see all this code because you are going to work inside template Haskell. Template Haskell is the mechanism that Haskell has to create functions at the compilation time. So all this work is at compilation time. It defines function at compilation time. So all these functions are going to be optimized, and we ended up with the optimized code, which is really fast. And that's the quick part of QuickFuzz. So, for example, to give looping, we can generate this code automatically. You end up with an instance, which, same as list, is going to choose between all these constructors. Here, they are very easy, just looping never, which is a single value, looping never, looping forever, and looping repeat for some int. So you ended up with a generator we choose between one of these values. As you can see, there is a new function which is sized, which we use to control the generation in order to not generate like infinite values or infinite list. And finally, for GIF file, we have to generate using arbitrary instances for every one of these types. And we end up with the same function. Here we are using the do notation, which is pretty common.
OK, so we are more or less finishing. So a little more about the results. We could generate a lot of different file formats, including source code, some images, documents, especially interesting the PDF one. We found like we able to generate PDF that can crash Chromium. In fact, it's the PDFume engine, and other type of PDF parsing files like beans and even the Apple one. So we have really good results using the Haskell code from someone else to find bugs and vulnerabilities in programs that we use every day, and they're supposed to be robust, but they are not. OK, in fact, QuickFuzz has, after the value generation, some part of file mutation that I'm not going to explain. But well, you can see here the two steps. Well, this part is just a limitation. If you want to QuickCheck a compiler, you can generate just nonsense code that is not going to pass the first stages of the compiler. So that's a problem, because you cannot test compiler if your code is just nonsense like this, and you try to use variables that are not defined. The compiler will say, I won't compile this, and you won't be able to reach some code of the compiler, so you won't be able to test it. So we have some workaround to fix this, but we want to save some time for the questions if you want. So we'll go directly to the future work. OK, we have a source code a generation with lightweight semantic constraints, as I quickly explained, because we want to test compilers and well, this is more or less a limitation of QuickCheck because you generate, as you can see, the code generates using some kind of local constraints, but in a program you have global constraints in which you have defined models and functions that you later use, and QuickCheck is just generating randomly, and it's not so efficient and effective for testing. We have the GADT automatically arbitrary instances, which is a challenge we're trying to address. We have the shrinking and mutation functions that we want to do in Haskell, and then some ideas about feedback-driven testing that, since I'm working on security, I would like that this fuzzer is currently blind because it cannot see what the program is doing, and maybe if you have a feedback from the program to the Haskell world, you can use it to test your program more efficiently. So thanks a lot for listen or talk. You can see the source code of our tool. You can just use tag to compile it, and you can see the list of bugs that we have that we found. And that's it. If you have questions, we have maybe time for one or two. Thank you. Yes, over there.
So for a lot of these recursive formats like source code,
Mm-hmm.
how do you tune the generator to give you like reasonable sizes, so not too short or not too long?
Well, the thing is that just quickly, we separate the constructors of a type. Some constructors are going to be recursive. For instance, some kind of value is included itself, and some are constants. So we just separate and say, if you have a constant, and if you have size 0, use the constant. And if not, use the other one, the recursive one. So it's more or less working, but it's not perfect, as you can imagine. OK, maybe one more, and then we are finished.
I don't know much Haskell, but I'm curious. Could you have used GHC generics instead of template Haskell?
Yeah, the problem with that is with template Haskell, we have a lot of liberty to take in order to generate a lot of functions. In fact, we are like not using Haskell because we move into a level where there is no typing at all. So what we gain with that is that we are faster than using generics. With generics, you are going to generate values more or less in the same way, but it's going to be slower. But it's going to be correct, well typed for that matter. So
OK, thank you. Sorry for the delay.